So what I thought we could do is we could kind of unpack this concept of bond polarity and how it leads to potentially molecular polarity. So on this page here, I've got our reminders on what our little threshold values on what determines the types of bonds. Once again, these are not absolutes. These are not set in stones. These are our guidelines, okay? But here I've given you, excuse me, 8 different types of molecules or compounds. We're going to write what the difference in electronegativities are between the atoms in the compound. And then as a result of that number, figure out what type of bond it is. And then on my Lewis dot structure, we are going to draw any dipoles if we have determined there is polarity to our molecule. And then looking at what the dipoles are, we're going to see if those dipoles cancel each other out to lead to a nonpolar molecule, or if they contribute to an overall net molecular dipole to create a polar molecule. So a lot of really fun things going on this worksheet right here. So let's get down into it. So the first one I have here is hydrogen, H2. You're like, great, difference in electronegativity. Let's see. I don't even have to look, guys. There's 2 hydrogens. Well, we will look because we're going to be good students here. And I got 2.2. 2.2 minus 2.2, y'all, the difference in electronegativity for that guy is, y'all, it's going to be 0. We like that because, it is definitely going to be a non-polar covalent bond. Non-polar covalent. Okay. So looking at this, I don't need to draw a dipole because he is nonpolar. And looking at him, let me see if I have an example. Let me see. Here we are. Look, there he is, right? I see no polarity in that bond, right? The electrons are shared equally, no dipole, right? So if I'm looking at the type of molecule here, there's no net dipole because there's no bond dipole. There's only 2 things in this molecule. So we're going to say that he is also a non-polar molecule. So this first classification talks about the specific bond inside the molecule, and this talks about the overall molecule, which the distinguishing between these 2 things may make a little bit more sense as we get down further here with us actually having more than one bond in these molecules. But we thought we'd start small because we like to do that sometimes. Okay, next one, we got hydrogen and iodine. We got hydroiodic acid coming in here hot. Well, hydrogen's electronegativity is 2.2. And iodine's electronegativity is 2.7. So 2.7 minus 2.2 gives us a difference of 0.5. Where does that put us? Here, into the polar. So congratulations, we have our first polar covalent bond between the hydrogen and the iodine. So here is my molecule, which also shows the one bond in the molecule. We said that iodine had a greater electronegativity, right? His electronegativity was a 2.7 compared to hydrogen's 2.2. So what that means is the electrons are going to be more strongly pulled by the iodine, so I can draw a dipole going towards the more electronegative atom in the bond. So that, remember, as a reminder, and we have a little picture up here to remind you, the direction where the arrow is pointing is showing the partial negative charge, the more electronegative atom. So if my molecule only has one bond and it itself is polar, congratulations, that molecule is polar. Okay, now we're getting into some molecules that have a little bit more going on besides just 2 atoms or one bond. So now we have CH4, right? Okay, so CH4, we've got, as you can see on my picture, we got 4 bonds, but they are all the same. They are all carbon to hydrogen bonds. So if I were to find the difference in electronegativities, I've got carbon, he's got 2.6. I've got hydrogen, he's got 2.2. So each one of those bonds between a carbon and a hydrogen is 0.4. 0.4 difference in electronegativity puts us polar. So each one of those individual bonds are polar. But now, how does that relate to the molecule? Well, out of the 2, hydrogen and carbon, we said carbon in the pair was more electronegative. So on this bond, I can draw a dipole going towards the carbon from the hydrogen. But then also on this bond, I can draw another dipole going from hydrogen to the carbon. And then on this guy, I can draw this dipole going from the hydrogen to the carbon. Oh, look at this. So yes, I do have polar bonds, but all those polar bonds cancel each other out. So there is no net direction where this collective amount of dipoles is trying to pull. Okay, so we would call this a non-polar molecule. And what we're looking for on our Lewis dot structure, which is what we're going to be able to use to determine if the molecule is polar or non-polar, is we're going to look for two things. Are there lone pairs on the central atom? And are the outer atoms different in some way? Well, here I have same outer atoms, and I have no lone pairs on the central atom. So those are the two things that are required to make a molecule nonpolar for these very simple Lewis dot structures that we are drawing in our first year of chemistry. So I have the same outer atoms, and I also have no lone pairs on central atom. You will not need to justify why you're classifying this molecule as nonpolar, but I do find, since we are using this page as, a thing to study from, some notes, if you'll say, that it's helpful to kind of remind yourself, what did I look at to determine whether it was nonpolar? Okay, awesome. The next one, we've got NH3, which we know is ammonia. So and in fact, I can pull out my CH4, right? My CH4, he looked like this, yes? So yes, each one of those CH bonds are polar, but since they are oriented to cancel each other out, the overall molecule is nonpolar. So now NH3, we've got NH3. There's my Lewis dot structure. I have 3 bonds, but they are all the same. Nitrogen bonded to hydrogen. So let's see what the difference in electronegativity is between a nitrogen and a hydrogen. Hydrogen is still 2.2. I feel like we should know that by now. You don't have to memorize this, but I feel like we've been using it in every example. And then nitrogen is 3. So 2.2 and 3, the difference in that is 0.8. So a 0.8 difference in electronegativity puts us at a polar covalent bond. So we will write polar covalent bonds. Polar covalent. So each one of these bonds in the molecule is polar. The more electronegative atom in the bond is the one that is going to get the direction of the arrow for the dipole, which is nitrogen in each one of these cases. So here's where the visual really helps. This is where it gets interesting. So it's like all of these bonds are going towards the nitrogen. And y'all, he got a lone pair on the top. We've talked about this. Look, here he is, ammonia. And there's his lone pair. So each one of these bond dipoles are pointing towards the center of that nitrogen, and the collective negative charge, the partial negative charge, is pulling up here towards the top. So we could say there's this net molecular dipole going up here. Off to the side, we can kind of draw it, right? To where this is the partial. That does look like an 8. That should be the delta. And it made me mess up thinking about how terrible my delta symbol looked like. That's the partial negative charge going up there. And then this is the partial positive charge going there. Yes? Okay. But as we can see that this is a polar molecule because of this net dipole that I was able to visualize and able to draw on here. Just looking at the Lewis dot structure, I can totally tell that this is going to be polar because I see lone pairs on the central atom. So LP on the central atom. Yes, cool. All right, next one down. This one is a little funny one. Y'all are already looking and being like, yes. So I have calcium oxide. Y'all are like, metal, not metal, ionic. Yes, but let's prove with our electronegativity values. I've got calcium. Calcium's got a 1. And then I've got oxygen. Oxygen's got a 3.5. So the difference between 1 and 3.5 is a 2.5 difference in electronegativity. And yes, we are totally going to be ionic. You're going to get that full transfer where calcium is going to kick off those electrons and oxygen will steal them. And these are our dot structures for our ionic bonds that we've grown to be able to love and draw on our own. So this is an ionic, right? And the type of molecule, it's not a molecule. It's not a molecule. We do not call ionic compounds molecule. We call them formula units. Thank you. So I do not have to classify polar or non-polar if I've got an ionic situation. All right, next one. This is super fun. I got CH3Cl. Well, here's my Lewis dot structure picture. You would be able to draw one of those if I asked you to. And here's a visualization. So I've got hydrogens. I got 3 of them, and I've got a chlorine here at the top. So I actually have 2 different types of bonds. I've got a carbon to hydrogen bond, and I've got a carbon to chlorine bond. So let's figure out the differences in electronegativities for each one of those 2 bond types. So if I had the carbon to hydrogen bond, we've done that bond before up here when we did CH4. It was a 0.4. But now the difference between carbon and a chlorine in the carbon to chlorine bond. Carbon is 2.6, chlorine is 3.2. So that gives us a difference in that bond, 0.6. Both the 0.4 puts us in the polar covalent, and the 0.6 is the polar covalent. So my CH bonds, we on the CH4 drew the dipoles going towards my carbon, right? But watch out here. Between the carbon and the chlorine, in this bond, chlorine was the more electronegative. So his dipole is going to be going towards the chlorine. To where, oh, they're not all going towards the center and canceling each other out. And if I bring my guy right up here, I can see that represented in this bond, yes? So I'm going to have a pull of my electrons towards this top where the chlorine is. So I'm actually getting a net molecular dipole in this direction, right? So what I have is a polar molecule. And the reason that it is polar in this case that caused a net molecular dipole is I had not all the same outer atoms. So I could say different outer atoms. Okay. So what makes a molecule polar are the 2 things we're looking for. We are looking for either different outer atoms or lone pairs on the central atom. If you have either one of those 2 things, your molecule, for only these simple Vesper shapes that we are doing in my first year chemistry course, your molecule will be polar. This does not apply to my expanded octets or more complicated Lewis dot structures. But for my basic simple shapes that we're learning in this course, yes, this will always work out for us, which is great. Okay. Next up, we've got CO2. We love CO2. That Lewis dot structure looks super familiar to me. I got carbon and 2 oxygens. So I have 2 bonds, but they are both a carbon to oxygen bond. So if I'm looking for my difference in electronegativities between carbon and oxygen, carbon is 2.6, oxygen is 3.5. So their difference is 0.9, which puts them polar covalent. Now in that bond, that polar covalent bond, the oxygen is the more electronegative. So I could draw a dipole going from the carbon to each one of the oxygens. Now looking here, those dipoles cancel each other out to where there is no net molecular dipole, which means this is a non-polar molecule. And the 2 features I'm looking for on this Lewis dot structure to have me classify something as non-polar is it must have the same outer atoms, and it must have no lone pairs on the central atom. So we're going to say same outer atoms, and then no lone pairs on central atom. Notice I'm saying central. I know these oxygens, they got lone pairs, but in terms of polarity for the entire molecule, that central atom is what I'm looking for lone pairs on. Because if we know lone pairs change the shape, and if I make this linear structure now go bent, then yeah, I'm going to have some sort of a dipole situation happening then. So if I were to find CO2, yes, he does have 2 polar bonds, both going towards the oxygens, but since they are going in opposite directions completely, the dipoles cancel each other out, so you've got a nonpolar molecule. All right, last but not least, we have water, H2O. So here's our structure of water. I've only got 1 type of bond, a oxygen to hydrogen bond. Hydrogen, I keep pulling this sheet out, 2.2. Oxygen is 3.5. So the difference between electronegativities of a hydrogen and oxygen is a 1.3. Wow, that's very polar. So this is a polar covalent bond, and I have 2 of them inside of my water molecule. Each one of these bonds, the dipole is going to be pointing up towards the oxygen. And because of its bent shape, you see, guys, they do not cancel out, right? In fact, I create a net molecular dipole with a partial negative charge up towards the top part where this oxygen is and his lone pairs that are creating this net dipole, right? And a partial positive charge down here where the hydrogens are. So we got a polar situation. But just looking at the Lewis dot structure alone, the thing that lets me know that this molecule is going to be polar is those lone pairs on the central atom. So lone pairs on the central atom. Okay, my handwriting is very sloppy today. Turns out when you have a pumpkin carving accident, it's hard to write with your pencil. I am fine. Do not worry. So what we've just kind of recapped here is how these bond electronegativity differences create polar or nonpolar bonds, and how all of them collectively can create a polar or nonpolar molecule. But in terms of reading from our Lewis dot structures, the good thing is that I just need to look at if there are different outer atoms or if there are lone pairs on the central atom. Those two things will make a molecule be polar.